Alright, so we continue our path through circle geometry, looking at angles in a circle. Before we do that, we need to do some definitions here of what is an angle in a circle called. There's two different types. There's first, ones in the center called central angles. And the central angle would look something like this right here. So there's your center dot, the letter O, and if you've got an angle going into the center, that's what a central angle looks like. Okay, like it says here, an angle created by two radii, so a radius and a radius connecting together makes an angle in the center. That's a central angle. The central angle must be doi at the center of the circle. So there would be an example, and you would call this angle AOB right there. That's the name of that center angle. And there are all those fancy words like subtends and stuff like that. So the chord AB has or subtends that angle. The other angle is called an inscribed angle, and inscribed angles are on the outside or the circumference of the circle. And so an inscribed angle is created by two chords. It looks something like this. So let's say you've got a chord here, and then there is the angle, but it's not going through the center, it's touching the outside circumference. So that angle CED is an inscribed circle. So central angle, inscribed angle. Okay, so let's name some of these central and inscribed angles. Let's look at the central ones first. So there's a red dot in the center there. They would call this angle DOE. Another one would be angle EOF. Another one would be FOC. Again, you can switch it around and call it COF as well. Another central angle, BOC or COB, either way. And you can see, you get the picture. Those are all central angles, and it's easy to name them. Alright, what about inscribed angles? Those are ones on the outside, there, and there. So you could have an inscribed angle here. This would be called angle BAF. So angle BAF would be one. Another one right there would be angle FEB. Again, any order, you could also call it BEF as well. And then here, ABE, and one in the corner here, which would be AFE. AFE. So, central versus inscribed angles. Okay, so there's a couple of rules about these angles, and this, again, is spread over two parts, this video. The first angle and circle geometry rule that we look at is that an inscribed angle of a semicircle is equal to 90 degrees. Here's what it means. So if you have a semicircle, and an inscribed angle is one that touches the outside. So if you make that an inscribed angle, and it goes through the semicircle, automatically that's 90 degrees. That inscribed angle is 90 degrees. Doesn't matter where you put it, it's 90 degrees, and there's the boxy thing to prove it. Move it somewhere else, 90 degrees. Move it somewhere else, 90 degrees. That's the rule. Now, it doesn't have to just be a semicircle. If it was a full circle, and that inscribed angle is just going through the one half of the circle like this, it's also 90 degrees. Okay, so basically the chord in this case is the diameter for that inscribed angle. Now vice versa, if the inscribed angle is 90 degrees, then the chord must be the diameter. So if we know that's 90 degrees, the inscribed angle is 90 degrees, the chord that it belongs to must be the diameter. So here you go. So if we know that's 90, then the chord that it belongs to has to be the center of the circle. That's the diameter. So CED is 90. That means this line here, CD, is going to be the diameter. Okay, let's not worry about the proof. Let's take a look at some problems here. So we want to find x. How are we going to do that? Well, there's a couple things we know right away. There, it's half the circle. There's the diameter, and there's an angle. So this is the semicircle theorem that we're looking at here. That is a diameter. There's the semicircle, so that's 90 degrees. If that's 90 degrees, and that's a 5 and that's a 12, do you know how to find this side? Yeah, you could use good old Pythagoras. Once we know what this full side is, this diameter is, can we figure out x? Well, what is x? X is a radius. And what do you know about a radius and a diameter? Well, half the diameter is the radius. So once we know the diameter, we just divide it by 2 to get letter x. So here's what they say. X, again, is the radius. So since the angle is 90 degrees, this must be a right angle triangle, which means we can use, there it is, bim, 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 bim. There we can use Pythagoras to figure it out, and then 12 squared, 5 squared, 144 plus 25 is 169, square root of both sides, you get 13, so that is 13. And if that's 13, the diameter is 13, half of that is the radius, and half is 6.5. So there you go. What about this one here? It's an angle we're looking for. Now, in this case, again, there's the diameter. So we're currently using a semicircle and only using half the circle here. That means this must be 90 degrees right there. Must be 90 degrees. Okay, we know that's 43. Now, some other things that we know here. This kind of bluish triangle here, I'll color this in, I'll draw it in. That triangle there is an isosceles triangle. Now, if you remember an isosceles triangle, the way we know it's an isosceles triangle is because that's a radius, that's a radius. Remember, isosceles triangles have two sides of the triangle being the same. So that's a radius, that's a radius. In isosceles triangles, the two base angles are equal. So that's 43, which means this has to be 43 as well. If that's all 90 and that's 43, to figure out x, what do we have to do? We just have to go 90 minus 43. So we just go, so it says again, because the angle at the top is 90, we just go 90 minus 43, and letter x is 47. Alright, so moving on to the next thing. Central angles that have equal chords or arcs are also equal. This kind of sometimes you call the butterfly kind of look to it, because it kind of makes a little butterfly. You'll see in a second. So suppose that there are two chords we draw, AB and CD, and let's pretend that they're both equal. If we were to, yeah, and even the arcs are equal as well. Either one. If we were to then draw central angles from those arcs, so like from there and there, like this, boom, and boom. What this is saying is the angles are going to be equal. So in other words, instead of what they have all here, all this wordy stuff, basically equal chords are going to give you equal arcs, which give you equal central angles. And so any variation of that, so central angles that are equal will give you the equal arc and equal chord. So it's good to know. Let's put this into practice with and again, here's the reason why, is because when you sort of rotate the chord around, the central angle doesn't get any bigger or smaller. It stays the same. So watch. Move the chord around, the angle stays the same. And again, vice versa. If the central angles are equal, then the arcs and chords must be equal. So they're all kind of three connected ideas all together. Okay, so let's try to find the value of x. These two chords are equal. And remember what we just said. If the chords are equal, the central angles are equal. Remember, it only works for the central angles. So if these two sides or chords are equal, their central angles are equal. That's 65. This then also must be 65 because they come from the same length chords. So again, since the chords are equal in length, the central angles that contain them are also equal. So therefore, x is also 65. Now over here, this one's a little trickier. There's a little trick here. We don't know right now if these sides or chords are equal. We don't have any information that any of the angles are equal yet. So we can't really do anything. But do we know, can we figure out what some of these angles are? Well, let me show you. It's one of the angle properties that hopefully you've learned before, but we're interested to know what this angle is. Angles that add up to a line, if you remember, add up to 180. So there's a line right there, the diameter, and all the angles in a line add to 180. Which makes sense, because the angle in a circle is double that, adds to 360. So what we can do is we can figure out what this is. So we can do 180 minus 48, and that's 68, to figure out what the remainder is. Well, when you do all that, you get 180 minus 116, which gives us 64 degrees. That means this is 64. And if that's 64, that central angle is 64, that central angle is 64, same central angles, equal chords. The opposite of this. Here it was equal chords, equal central angles. The opposite is true, equal central angles, equal chords, which means this must be 12. Okay, let's just let the computer say all that. Pretty much what I just said. That's some fancy language. So the sum of all the angles in a straight line here add up to 180. So that's 64, which means the missing angle must be 12 because of that little rule that I just said. Central angles and chords. Central angles that are equal, the chords must be equal too. Okay, that's not your homework, that's something else. So here's your skill testing question. So find x and y here. So there's x, there's y's. Find what those guys are. And here, find side x once we know that these two angles are that. There you go. I think it's pretty straightforward, and hopefully you do all right with it. Talk to you later. Bye-bye.